Hello everyone, I hope you guys are doing good. So in this lecture I'll be covering nonlinear regression functions, and the specific nonlinear functions that I'll be taking a look at are the polynomial and logarithmic functions of a single independent variable. So the outline of this lecture is as follows. So first of all, we will look at the general conditions which underlie nonlinear regression functions, and then we will move on to nonlinear functions of one variable where we will mostly be looking at polynomial and logarithmic functions. So far we have looked at linear functions mostly when we have been dealing with ordinary least squares, but the linear approximation is not always a good one, and that is simply because some relationships between two variables might not be linear at all. So if you look at the relationship between income and education, maybe that's not a truly linear relationship, and in that case a multiple regression model can handle regression functions which are non-linear in nature as well. So we will have to revert to those kind of models, because when we know that the relationship between two variables is not linear, we should not be applying a linear model to actually study the relationship between those two variables. So for example, if you take a look at the example that we have been looking at in the previous lectures as well, which is the relationship between the student-teacher ratio and average test scores in the school, you will see that if you simply look at the scatter plot, you will see that this relationship might actually be a linear relationship, but this might not be true for all relationships between two variables. For example, if you are looking at the relationship between district income and test score, now this relationship, if we just look at the scatter plot and we try to plot a line of best fit through that scatter plot, this relationship does not look like a linear relationship at all. So if we actually take a closer look, it might be the case that with initial increases in income, the test scores might increase very sharply, but after a certain point, increases in income will not really lead to higher increases in test scores. So that is the kind of relationship that we are looking at, meaning think of diminishing marginal returns. So when you guys studied diminishing marginal returns, you were basically looking at the slope, a higher slope in the initial part of the relationship and a lower slope in the later part of the relationship, and this is the kind of relationship which looks like between district income and test scores. So in this sort of an example, trying to fit a line of best fit which is linear over the scatter plot might lead to wrong conclusions. So if a relationship between y and x variables is non-linear, the effect on y of a change in x depends on the value of x, that is, the marginal effect of x is not constant. So think of this previous example. So over here, a small change in x variable will cause a large change in the y variable in the initial part of the distribution. But at this end of the distribution, a smaller change in x will probably have no change or very little change in the y variable. So the marginal effect of x is not constant. So a linear regression is misspecified in this scenario, and a functional form would be wrong. And given that, the estimator of the effect on y of x would be biased if we actually try to fit a linear functional form. So the solution would be to estimate a regression function that is non-linear in x. So an important point to note over here is that the assumptions of OLS remain the same even for the nonlinear population regression function. So we will basically have to still follow the same set of 4 assumptions. The first one is that the conditional expectation of u given x's is equal to 0, so that still remains the same for even for nonlinear functions. The second assumption is that all the x's and y's are identically and independently drawn, so that also remains the same. Big outliers are rare, meaning the kurtosis is not infinite, so that also remains the same, and there is no perfect multicollinearity between the variables. That also remains the same. So your 4 classic assumptions of OLS still remain the same for nonlinear functions. So the question that arises now is that the change in y, how do you calculate the change in y associated with the change in x1 holding all of the other x variables constant? So over here you have your change in y, and how will you calculate that? So in the first function you will have all the values of the other variables from x2 to xk, and you will have x1 plus the change in x1. So this change in x1 is what you are mostly concerned with, because that change in x1 will be causing this change in y. So you have this function over here in which you will have the value of x1 with the change in x1, and from this function you will subtract the function in which you will have all the initial values of all the other variables as well as x1. So remember that none of these other values of other variables will change over here, because you are just looking at the relationship between change in x1 and change in y. So in order to isolate the change in y, you will have to basically subtract this function from this function. So this is just a formal way of saying the same thing. If you want to find the change in y associated with the change in x1 holding all the other x's constant, you will have to basically take the difference between the value of the population regression function before and after changing x1, so utilizing this identity over here, and the corresponding difference between the predicted values of y can be calculated from this identity over here. So in this lecture, we will mostly be looking at polynomial functions and logarithmic functions. What are polynomial functions in x? So they basically mean that the population regression function is approximated by a quadratic, cubic, or a higher degree polynomial. So the key thing to keep in mind over here is that if you go back to your high school calculus or high school geometry, you will basically think about the quadratic function, and the quadratic function basically captures the curves in the relationship. Whenever there is a quadratic function, it basically means that the relationship between two variables is no longer linear. So that is what we are dealing with when we are dealing with the case of polynomials. For our logarithmic transformations, so when if y and x are transformed by taking their logs, we are dealing with the percentages interpretation that makes sense in many applications. So if, for example, if you want to look at the relationship in terms of percentage change, if you go back to the example of price elasticity of demand, and you're looking at how much will be the percentage change in quantity demanded if there's a specific percentage change in price, then a logarithmic function might actually be a better function to use, because you're mostly dealing with the percentage changes in both the variables when you are dealing with the case of elasticity. So this is the example of a polynomial function. So what we have over here is that we have x as an explanatory variable, but we also have x square as an explanatory variable, and we can have polynomials up to the degree r, meaning over here we will have x to the power r if we wanted to include that many number of polynomials. So this is just the linear multiple regression model. Basically looks like that. We just are adding polynomials of higher degrees for the same variable x in this regression model. So the key things to keep in mind is that the estimation, the hypothesis testing, the confidence intervals, and all the other things which you are dealing with the OLS regression model, the linear regression model, remain the same even with this model when we are including polynomials of higher orders. The coefficients, however, are more difficult to interpret in the case of in the inclusion of polynomials, but we will take a look at that in this lecture later on, and how to interpret the coefficients. So let's get back to the example of the relationship between income and test scores. So if the scatter plot is telling us that this relationship is probably not a linear relationship, then we might have to go with a quadratic specification, meaning you have test score as the y variable, and you have income as one of the variable, and you can include income square as the second variable. Or you can also go with the cubic specification, meaning you can also have income to the power 3 as the third variable. So once again, why are we doing the quadratic or the cubic specifications? Because we want to capture the slopes in the relationship. We want to capture the different slopes in the relationship. If we actually impose a line of best fit which is straight, which is linear, we will not be able to capture any slopes in the relationship. But while using quadratic and cubic specifications, we will be able to capture the slopes in the relationships. So how do we do that in STATA? So you can simply calculate a new variable. For example, if your variable for income is AVGINC, you can create a variable AVGINC2, which is basically the square of AVGINC. AVGINC is being multiplied by itself, meaning this AVGINC2 is the square of AVGINC. Then you simply type in your regression command, reg. Test SCR is your y variable, AVGINC is your first explanatory variable, and AVGINC2, which is the square of AVGINC, is your second variable. So keep in mind that this is the specification of the quadratic model. If we wanted a cubic model, we will have another variable added next to AVGINC, which will be the cube of AVGINC. So let's take a look at the coefficient of AVGINC2, which is the square term in this regression equation. So we can see that the t-stat is basically telling us that this is significant even at the 1% level of significance. So the coefficient over here is a negative coefficient, and it is significant at the 1% level of significance. So this high level of significance tells us that it was a good idea to actually include the AVGINC2 variable in this equation, because there were non-linearities which are being captured by this new variable in this relationship. So the way to find out what level of polynomial you should add in your regression equation, you basically have to keep on adding the polynomials of higher and higher order. So for example, if you saw that AVGINC2 is highly significant, the coefficient of that is highly significant, you can try to add AVGINC3, which will be the cube of AVGINC, and try to see if that is also, if the coefficient for that is also highly significant. If it is, you can even add AVG INC 4, which will be AVG INC to the power 4. So you keep on adding polynomials of a higher degree until you see lack of significance. So this is what we so all of these coefficients are what we got from the previous slide, and the terms in the brackets are the standard errors. So if we were simply not including the quadratic term over here, the income square, and we plotted a linear regression function, this is the line of best fit we would have got. But in the case of the quadratic regression that we just ran, the line of best fit that we get is actually a curve, and this is, to me at least, better capturing the variation in this relationship. So you can see that the slope is higher in the initial part of the distribution and it is lower at the later part of the distribution. So if you see this equation over here, 607.3 plus 3.85 income minus 0.0423 income square. So think back to your classic quadratic equations. If you take the double derivative of this equation with respect to income, you will actually get a negative number because of this negative sign over here. And whenever you take the double derivative and you get a negative number, it simply means that the function has a maximum value. And you can actually see over here that this quadratic function has a maximum value somewhere. So this tells you a lot about the relationship, whether this function has a maxima or a minima. In this case, this function has a maxima. So you can basically think about, try to apply the knowledge that you have gained previously when you were learning about quadratic functions and apply the same knowledge over here. The point, to summarize all of this, it basically shows that the quadratic function is a better fit over the scatter plot than the linear regression. Now, how do we compute the effects for different values of x? So remember that because we are dealing with a non-linear relationship, the marginal effect of x is going to change for different values of x. For lower values of x, the marginal effect on y would be higher, and at higher values of x, the marginal effect of on y would be lower, because the slope will actually decrease as we increase the value of x. So what is, if for example we are trying to find out what is the predicted change in TestScore for a change in income from $5,000 per capita to $6,000 per capita, we will basically plug in the value of $6,000 per capita in one of the functions, and this is how we do it. So these are all the coefficients that we obtain from the quadratic regression equation, and we will subtract from this function while using the value of 5,000 per capita over here. And when we do that, we will actually see what the change in TestScore will be, and the change in TestScore is 3.4. So remember that the graph over here is thousands of dollars. So the income is in thousands of dollars, so that's why we are not using 6,000 and 5,000 over here. We are instead using only 6 and 5 over here. So this square term over here and over here means that the marginal effect of x is going to change. If the square term was not present in this regression equation, the marginal effect of x on y would remain the same throughout. But that is why that is what we wanted. We wanted the marginal effect to change because we wanted to see how a curve could better fit the scatter plot. So, but in this scenario, for a change in income from 5,000 per capita to 6,000 per capita, we find that the change in test score comes out to be 3.4 points. Now, given this equation that we estimated for the test scores, meaning for the predicted test scores, let's see what the change would be from 5,000 to 6,000. We already calculated that. When the income changes from $5,000 per capita to $6,000 per capita, the change in test score will be 3.4 points. When the income changes from $25,000 per capita to $26,000 per capita, the change in test score will be only 1.7 points. And you can simply follow the same kind of logic that we did for 5 to 6 in the previous slide, and you can plug in the numbers 25 and 26 in the two functions and then subtract them from each other to see that the change in test score will only be 1.7. Now, if we take if you try to calculate what will be the change in test score if the per capita income changes from 45,000 to 46,000, you will actually see that the change will actually come out to be 0. So this clearly shows that as income is increasing, the effect on Y or the test scores of that change in income is getting smaller and smaller. So once again showing diminishing marginal returns. So the effect of a change in income is greater at low than high income, and you basically see a declining marginal benefit of an increase in school budgets. So if we wanted to find the effect of a change from 65 to 66, can we do that? The answer is that we cannot, because if you look over here in this scatter plot, we don't even have data from for 60 to 65. So any sort of extrapolation outside the range of the data can actually give us wrong conclusions, because we actually don't know what the predicted values of Y in that range of data of X will be, because we never had that range of data. So in this example of STATA, we are also including a cubic term in the regression equation. So we basically first created the AVG-INC3 variable, and then we are including that in the regression equation as well, and these are the results of that. So over here you can see that the AVG-INC3 variable is also significant, at least at the 5% level of significance, which means that including this is probably gives us a better and more accurate estimation of the relationship between average income and test scores. So if we as researchers were trying to test the null hypothesis of linearity against the alternative hypothesis that the relationship, the population regression is actually a cubic relationship, then we will have to test the null hypothesis that the population coefficients on income square and income cube are equal to 0 against the alternative hypothesis that at least one of these coefficients is non-zero. To do this test, you simply type the test command in STATA and then type in your quadratic and cubic variables after that. So according to this test, the null hypothesis is rejected at the even at the 1% level of significance. So it simply means that the alternative that the polynomial is of a degree up to 3 is the true relationship. And the relationship between average income and test scores is not a linear relationship. So to summarize all this, the estimation by OLS so we basically have to estimate any sort of polynomial regression functions by OLS. The assumptions of OLS still hold even for these nonlinear relationships. The coefficients are slightly harder to interpret, but we have shown in these slides that they can still be interpreted. The important thing to remember is that the marginal effect of x on y will change with different values of x. To interpret the estimated regression function, you can plot the predicted values as a function of x. So whenever you look at the line of best fit, or in the case of polynomial functions, the curve of best fit, it actually gives you a fairly good idea of what the relationship actually looks like. So it's always a good idea to do that. And then you can compute the predicted change in y over change in x at different values of x. So change in y over change in x is simply the marginal effect of x on y. Hypothesis testing concerning the degrees of polynomial can be done by using the t-test and the f-test on appropriate variables. So for example, t-test is important because you're looking at the level of you're looking at whether you reject or fail to reject the null hypothesis that the coefficient of the polynomial is equal to 0. And the f-test, like I showed in the previous slide, can be used to actually see to check against the null of linearity. If you're if you're checking against the null that the polynomial, the coefficients of the polynomial variables is equal to 0. So how do you choose the degree of R? Meaning what is the highest degree of polynomial that you go to? So you can do 3 or 4 things to actually decide that. You can plot the data and see how many curves or what kind of a relationship you actually see from the data. If you see only one curve, a quadratic function might actually be a better idea. If you see 2 curves in the relationship, a cubic function might be a better idea. So and then you can also look at the t-test and the f-test between the different coefficients to actually determine what is the highest degree of R that you go to. You can also check the sensitivity of estimated effects, meaning how they actually change when you include or exclude a degree, a higher degree polynomial in your equation. And finally, you can use your judgment, meaning you can use the economic theory underlying the relationship to actually see what polynomial you end up including in your regression equation. So now we turn our attention to logarithmic functions of y or x. So ln x or log of x is the natural log of x, and logarithmic transforms permit modeling relations in percentage terms. So like I mentioned earlier, if you are interested more in looking at the percentage change in x and how that will result in a change in y, or how a change in x will result in a percentage change in y, or finally how a percentage change in x will result in a percentage change in y, we can resort to the logarithmic functional form, and the interpretation will be pretty easy in the case of logarithmic functional forms, which is kind of different from the polynomial functional forms where the interpretation becomes a little bit tricky. So why is the interpretation in this case a little bit easier? Because the logs are designed in such a way that if you are looking for how the log of x plus a small change in x minus the log of x, what is this equal to? It turns out that it is actually equal to the change in x divided by x. So whatever the change in x over here is, if you divide that by the initial value of x, you actually get the value of this calculation over here. If you put that into practical example, if you take ln 1.01 and you subtract ln the log of 1 from it, what does that mean? It would mean that the change in x is equal to 0.01 and the initial value of x is equal to 1. So this should be equal to 0.01 divided by 1, and it is kind of equal to that. Not exactly, but for a rough idea, it is equal to 0.01. Similarly, if you look at the log of 1.1 minus the log of 1, it would mean that the initial value of x is 1, and the change is equal to the change in value of x is equal to 0.1. So it turns out that this is equal to 0.1, or very close to 0.1, is actually equal to 0.0953. But as a rough guide, this is the beauty of using the logarithmic functions, because it can basically tell you percentage change, meaning change in x divided by the initial value of x. So when we are dealing with the log regression specifications, we need to be very careful about which kind of specification we are using, because the interpretation will change depending on what kind we are using. So there are three classic examples or classic forms of log regression specifications. The first one is the linear log, in which the y variable is not logged but the x variable is logged. Then there's the log linear, in which the y variable is logged but the x variable is not logged. And then there's the log-log specification, where both the y and the x variables are logged. The interpretation of the slope coefficient will be different in each of these cases, and we can basically figure out what the interpretation will be while using the before and after rule to figure out what the change in y is for a given change in x. So first of all, we will take a look at the linear log population regression function, in which the x variable is logged but the y variable is not logged. So this is the before equation, and the after equation is as follows. So what this simply means is that you're looking at how a change in x is going to cause a change in y. So this becomes your after equation, and this becomes your before equation. If you subtract the before equation from your after equation, you get change in y equals to beta 1 multiplied by log of x plus change in x minus log of x. So from the previous slides, we know that this identity over here, which is being multiplied by beta 1, is equal to change in x divided by x. And we actually did a couple of examples in the 2 slides before which actually shows this relationship, So what this simply means is that we can substitute this identity over here or over here by change in x over x. So then change in y ultimately depends on beta 1 multiplied by change in x over x. So this becomes way more easier to interpret than if you write it like this. But this is the beauty of logarithmic functions, that we can actually simplify the interpretation to this relationship. So this also means that if you take everything to one side and keep beta 1 on the other side, it means that beta 1 is equal to change in y over the percentage change in x, and this will be true for small changes in x. So the linear log case will then be, for small changes in x, the beta 1 will be equal to change in y over the percentage change in x. So change in x over x multiplied by 100 gives us the percentage change in x, which means that a 1% increase in x, meaning multiplying x by 1.01, will be associated with a 0.01 multiplied by beta 1 change in y. So remember that the change in y is not in terms of percentage over here, only the change in x is in terms of percentage. So 1% increase in x, meaning a change in x by 0.01, increase in ln x, which gives us a change of 0.01 beta 1 increase in y. So sticking to the example of test score and the relationship with the test score between test scores and income, if we take the log of income and include that in the regression equation and estimate it, we get these coefficients over here. So 557.8 is the constant or beta naught, and 36.42 is the coefficient of the log of income. So what we see over here is that we can easily interpret the results of this equation, and we can say that the 1% increase in income is associated with an increase in test score of 0.36 points on test. So once again, just using this identity over here, that a 1% change in x results in a 0.01 beta 1 change in y. So 1% increase in income over here will result in a 0.01 multiplied by the beta over here, 36.42 points on the test. Keep in mind that the interpretation of standard error, confidence interval, and R-square all remain same over here, because that the unit of y remains the same, which is the test score. So how does this compare to the cubic model? So if we plot both the linear log specification and the cubic regression, they pretty much look the same. The only difference as far as I am concerned would be the interpretation of the linear log regression is way more easier than the cubic regression. And that's a key point, because as researchers you want to simplify the results of your empirical analysis as much as you can for the reader. So a linear log regression then is more of an easier, easily interpreted specification. So remember that we get this easily interpreted result in the case of linear log because we are dealing with percentage change in x. So if we go back one slide, you will see that in the case of polynomials you are getting multiple coefficients based on the degree of the polynomial, but over here you only get one coefficient. So this does not imply that this is a linear relationship, but this only implies that the relationship between test score and log of income is a linear relationship, but the relationship between income and test score is not a linear relationship. What that simply means is that if you're thinking of percentage change in income, so if you have a lower level of income, a 1% increase in income would amount to a lesser change in income. And that lesser change in income will result in an increase of 0.36 points on the test. If you are at a higher level of income, a 1% change in income will amount to a greater absolute change in income. But even in that case, the change in test score will remain the same, which will be 0.36 points. So this actually shows non-linearity in the relationship between income and test score, but linearity in the relationship between log of income and test score. Next, we will take a look at the log linear population regression function, and over here the y variable is logged while the x variable is not logged. So equation B is the before equation and equation A is the after equation, in which we are trying to see how a change in x will cause a change in y. So if we subtract A minus B, the after minus before equation, we get this identity over here, which simply means that this part of the identity, ln y plus change in y minus ln y, can be simplified to change in y over y. By now we pretty much know how this happens. which once again means that beta 1 will be equal to percentage change in y divided by change in x, and that will hold true for small changes in x. So just keep in mind that the interpretation changes slightly over here from the linear log specification. So if this is the regression that we are estimating for small changes in x, the beta 1 will be equal to percentage change in y divided by change in x. And so if we multiply the change in y over y by 100, we get the percentage change in y, which means that the interpretation then becomes that a change in x by 1 unit is associated with 100 multiplied by beta 1% change in y. So a 1 unit increase in x will result in a beta 1 increase in ln y. So keep in mind that the relationship between x and log of y will be a linear relationship because beta 1 will remain the same throughout, but the relationship between x and y will not be linear because a 1 unit increase in x will result in 100 multiplied by beta 1% increase in y. So what are the units of u, the residual, and the standard error of regression in this scenario? So the units will change over here because remember that we have log of y as the dependent variable. So the units of u and SER, the standard error of regression, will also be in terms of log of y rather than in terms of y. The third kind of logarithmic specification is the log population regression function, and over here both the y variable and the x variables are logged. So equation B is the before equation and equation A is the after equation. If we subtract the before from the after, we get this relationship, and we have seen, as we have seen previously, this side can be simplified to change in y over y, while this side can be simplified to change in x over x. So this is a very neat simplification over here, where beta 1 will be equal to the percentage change in y divided by percentage change in x, and this will hold true for all small changes in x. So if this is the regression equation that we are estimating, and for small changes in x, beta 1 will be equal to percentage change in y divided by percentage change in x. If you multiply the change in y divided by the initial y by 100, you will get the percentage change in y, and 100 multiplied by change in x divided by the initial x will give us the percentage change in x, which simply means that the interpretation becomes a very neat sort of interpretation, and it will be it will go as 1% change in x will be associated with a beta 1% change in y. So this sort of log specification has the interpretation of an elasticity. So go back to the example of change in price and change in quantity demanded. So essentially, when you are calculating elasticity, you are taking a look at the percentage change in price and how is that causing a percentage change in quantity demanded. So if that is the case, if you are looking at the relationship between price and quantity demanded or quantity supplied, a log specification will make the interpretation really neat and simple for the reader. So let's try this log specification in the case of test scores and average income. So when we do that, we were trying to estimate this equation, and when we do that with the help of STATA, we get these coefficients over here. So remember that the relationship between log of income and log of test score will be a linear relationship in this case, but the relationship between income and test score will not be a linear relationship. So the interpretation from this results is that the 1% increase in income will be associated with an increase of 0.0554% in test scores. So if, for example, the income increases from 10,000 to 11,000, which means that the percentage change will be 10%, then the test scores will increase by 10% multiplied by 0.0554, meaning 0.554%. So if the initial test score at the average income of 10,000 was 650, then it would mean that the test score will increase by 0.0554 percent, which will give us the change in test score of 3.6 points. So the question then becomes, how does this compare to the log linear model? So if you look at the log linear model, so over here I have log of test scores as the variable on the y-axis, and because the test scores are logged over here, that's why the log linear model gives me a linear relationship, while the log specification gives me a curve. Keep in mind that the x variable over here on the x-axis is not logged, so the log linear gives me a linear relationship, while the log gives me a curve. So it all depends on what you have on your vertical axis, on your x-axis, and that will determine whether the specification is a straight line or a curve. So if you go back to our cubic or linear log specification, both of these, log linear and log do not fit as well as the cubic or the linear log specification. It'll be easier to see when you put them side by side. So to summarize the logarithmic transformations, there are three different types. There's a linear log, the log linear, and the log specification, and the interpretation for all three of these cases will be different, so you have to be very careful about which one you are using, and careful about interpreting the results from the logarithmic transformation, because you want to be precise about that. The regression will be linear in the new variable, whether it is log of y or log of x, and the coefficients can be estimated by OLS. So you are still sticking to OLS estimation. Nothing has changed over here. The hypothesis testing, confidence interval, and everything else related with the OLS post estimation remains the same over here, and you can refer to my earlier lecture about hypothesis testing and confidence interval after a single regression and also multiple regression to get an idea of what those are. But the interpretation of beta 1 differs from case to case, meaning whether it is a log linear, linear log, or a log specification. And whatever the choice you make, meaning whichever logarithmic transformation you actually choose, should be guided by the economic theory between the two variables that you are trying to study. And you can also see the relationship by plotting the predicted values, and you can also do hypothesis testing between the three models, between the coefficients of the three models, to actually see which one would be the best one. So what I mean by that is that, for example, one way of looking at it would be if the R square actually increases from the linear log to log linear transformation, then it would mean that the log linear transformation is a better transformation. So this pretty much ends the lecture for this part of chapter 8, this part of nonlinear regression functions. Keep an eye out on my other part of the nonlinear regression functions lecture, which will basically cover the interactions between independent variables. So Thank you all for listening. I hope this added to your understanding of nonlinear regression functions, and take care.